investigate the natural base E. You should have learned about E before. You might not remember much about it. We're going to derive it. We're going to do this by using an exponential formula. Before I talk about this compound interest formula that's written here, I want to talk about the formula that comes before that, because you will need this other formula I'm about to write down for, you're going to have like a problem solving worksheet. And it's not due for 2 classes. It is posted today. It's not due for 2 classes. But you'll need this formula for the problem solving worksheet. It's exponential modeling, or for growth or decay. So you should have heard that term before, yeah? Science class, previous math classes. And there's a formula for this. We're going to start with y equals a parenthesis 1 plus or minus r to the t. And in this formula, the a is the initial amount. The R, anybody want to guess what R stands for? It's not radius. Rate. So, you know, they're going to tell you a percentage, but this is going to be the rate as a decimal, not percent. Okay, so if it's 5%, you'd write 0.05. The T, anybody want to guess what T is? Yep, time. And then the Y would be the new amount. Now this is for growth or decay. If we're talking about something that's going up, that's increasing, we would use the growth and we would use plus. If it was decay, you would use subtract. So that's what the plus or minus for. So you will need that exponential growth or decay model in part of in one of your assignments. Today, when we are deriving this natural base E, we're going to use a more specified version of this. It is a growth, but it's specific to compound interest. So interest could be something that we, you know, put money into a savings account and they figure out your interest per year, once a year. But sometimes they will do what's called compound interest, where they're going to compound it. They're going to do the interest multiple times throughout the year. So when we have a number of times per year that something's being compounded, we have this extra variable. So N stands for the number of times per year. And this N is in 2 different places. It's underneath the rate, which is the exact same as the other equation, and it's multiplied by the time, which is the exact same, you know, T is time, just like the other one. You just have this extra N thrown in there. It's only plus because this is compound interest, which increases money. And there's a P that's different than the lowercase a, and there's an A that's different than the lowercase y. So the y and the lowercase a in these, they're just random variables, like y equals mx plus b, the M stands for something. Over here, the Y and the capital A are basically the same thing. They're the new amount. And then the P is the same thing as the little a. It's the initial amount, but it actually stands for a word called principal. And not like Mr. Brown, sorry. Not like Mr. Brown, but like a principal is a vocab word given to that initial amount that you put into the savings account. Okay. So to investigate this natural base of E, we are going to invest $1 for 1 year at a rate of 100% compound interest. All right. And then what we're going to do is we're going to change how many times this compounding period is happening per year. We're going to increase it. We're going to see what happens to the final amount in the account after 1 year when we change the compounding period. So for the first one, we are doing A equals, we're going to do, our initial amount is $1. 1 plus, our rate is 100%. So what is that as a decimal? Just 1, right? So we're going to do 1 over, and then how many times per year, sorry, per year, yearly is once. So my n is 1. And we're going to take that to the n1 times for 1 year, 1. Okay, got lots of ones. Simplify that just a little bit. We're taking 1 multiplied by 2 to the first power. It says 8 decimals. There we go. So we'll do the second one. Still $1 invested. It's still 1 plus. We're still doing 100%, but this time we're going to compound it semi-annually, which is 2. So my n value is 2. And then we raise that to the 2 times 1 power. This one I could probably do in my head, but the rest of them I'm going to start using my calculator. This one would be like 1.5 to the second power. Anybody know 15 squared? 2.25. Yeah, 225, yeah. Okay, so after this, I'm not going to do the work for you. I'm going to probably do one more, but then you're going to spend some time with your calculator and figure out the rest of these. So for the next one is quarterly. How many times per year would quarterly be? 4. So we're going to do $1, 1 plus a fourth to the 4 times 1. There's no reason to do this simplified step if we're going to use the calculator the whole time. If you do it in fraction form, your answer usually comes up as a fraction if it can. So I would just do it in decimal form, or actually do the way I type it in my calculator. Actually, I have a calculator open. I'm going to type in, I don't even need to type the first one in. I did, but I'm not going to do it every time. I'm going to type it in this way rather than doing like the actual fraction. I'm going to type it in division. And then it'll give me a decimal answer. So 2.4414. 0.625. So you're going to fill in the rest of these. When it comes to the ones that it just says like a bigger number, a larger value, you get to pick whatever larger value you want to. Okay? I am going to pause my screen. I'm going to still do it on the video, but I'm not going to talk through it. So start filling yours out. Bless you. Paper. Just want to write down paper. Otherwise, you try switching over to a different. Or is it just like it's still just? Okay. It was just slow. I didn't know how big you were going to go. What did you choose for this larger one? Just a ton of like 99,999,000. Is that what you wrote? 99 million. Because all of these I'm just walking around, kind of looking at those of you that got to the larger one. I'm just curious, like what larger numbers? Because I didn't pick any larger numbers yet. Coming around to see what you chosen. Oh, because you have it 40 million. 80 or 60? Just 10 and 12 zeros and the big numbers. Okay, so those of you that have chosen your, I'm going to say it over here. Those of you that have chosen your larger numbers yet, I haven't on my screen, so I don't have it up yet. But those of you that have chosen your larger numbers, we are finding what number it is getting closer and closer and closer to. If you don't have that answer yet, pick another larger number while you're waiting. If you don't know the answer to that question yet, pick another larger number. If you haven't gotten there yet, then keep going. But if you don't have the answer to my question, what number is it getting larger and larger and closer to? Sorry, closer and closer to when you pick up larger numbers. Try another number. So if you can't tell what number it's getting closer and closer to, try 500 billion. Well, we're gonna have like 8 digits that it's gonna get closer to. So if you go all the way 8 digits, say 4 million. Okay, so if you are a little bit slower, that's okay. I'm just going to pick some numbers that I saw around the room as I walked around. I saw a lot of people went to 40 million next. Some people did 50 million. So if you did 50 million, you just have a slightly different number. But that's going to be 1 plus 1 over 40 million to the 40 million. And then how about I'll do 100 million? So when I get to here, I can definitely see a lot of numbers showing up over and over and over again, but I still don't know what number it's approaching. So I'm going to try a bigger number. I'll probably just use the same equation and add in another zero. So it'd be like 1 billion. So I'm just going to recopy that last one and just plug in another zero. Still not helping me. I'm going to do, how about another 2 zeros? Why not? I mean, we try to find this when it's going to infinity. You can't have a too small of a number. So I just put in 2 more zeros. So I'm doing 100 billion. Okay. How about anybody do anything bigger than 100 billion? Was yours bigger, Marie? You had, would you have 12 zeros or 16? I don't remember what your last one was. 16 zeros. Okay. Hopefully I can count. Oh, or did you type it in as like times 10 to the, you type it in that way? That's a smart way of doing it. Let me do it that way. Save me a little time. Nope, I typed it in wrong. What did I do? Never mind. I'm just going to do it by hand because I typed it in wrong and I don't want to keep wasting time. 1 divided by. What am I typing in wrong? I'm typing something in wrong. What did you get when you typed that in, Marie? Okay, so that's what's happening. It's too big. Because I was going to say, I don't think I'm typing it in wrong. I'll get rid of a couple zeros. What was the last one I did? Billion, 100 billion. How about 100 trillion? 100 and then 1, 2. Okay, that gave me an answer. So 2.718281828. Okay, I'm going to be done at this point. Why can I be done? Because why? Somebody said something. Oh, it's repeating. So if I do anything bigger, it's going to keep repeating. So it's approaching this number. Now, these don't have the same answer. They don't have the same answers. Just after that, I can't even see any more decimals on my calculator. And after 8 decimals, that's a very, very small, insignificant difference. So we are approximately getting there. So if I were going to say, as n approaches infinity, this number is approximately getting to be about 2.718. Would that be a good enough? I mean, I could write the whole number out there. This is like really, I mean, not the entire number, but this is a lot of the number. Do you know any other number that just like the decimals keep going and just don't really have any pattern and they're just like decimals that go on forever? Does that sound familiar at all? What is it? Pi, yeah. So this number is just like pi. It's not pi, but it's just like pi in the sense of it's an irrational number that shows up often in mathematics and nature. So because it's so important, this number is given a letter, just like pi is given a symbol. This is given E. So when we talk about E, we are talking about this natural number, 2.718281828, whatever else comes after that. I, in class, only use 2.718. Or if you go to your calculator, there's actually second, and then there's an LN button on the first column, second LN. Second LN, and then E to the first. There's the number. Yes, Christopher? Yes, it's also E. But we are going to use the one that I mentioned more often than second division. So you can also do second division that automatically puts the 1 in for you. So there's the other place that you see the number. So that's E. And we have derived it by using compound interest. We're going to derive it one more time. Again, you will not be tested on deriving it, but now we've gone over compound interest and how to use that formula for future exponential questions. Here, I'm going to go over factorials. Factorials are not in this chapter. We didn't even do the chapters that chapter that has factorials in it, but you should have seen them prior. Yes? Maybe? Well, so we're going to go over factorials really quick going over it. When we have, I'll come back to this statement in a moment. When we have the exclamation point, it's not like saying n. It's called n factorial. So factorial means that we take whatever that number is, and I'm going to look at 5 because it's easier to explain when there's more numbers. And we take that number and we multiply by 1 less than that number. So 5 minus 1 is 4. And then we take 5 and we multiply by 2 less than that number, which is 3. And then we take it and we multiply by 3 less than that number. And then we multiply by 4 less than that number. Oops. 1. So it's basically 5 times 4 times 3 times 2 times when you get to 1, you stop. Those are factorials. So if you see that symbol, it means do that. Now, as we're building, going higher and higher in factorials, you can see that there's a pattern where we are taking the previous factorial and multiplying by the next number. So for like 3 factorial, I just take 2 factorial and multiply by 3. Or for 3 factorial, I just take 4 factorial. I take 3 factorial and multiply by 4. Like that's how we're getting the factorials a different way. And then when we look at this pattern here, this is like multiplying by 2, multiplying by 3, multiplying by 4, multiplying by 5. So we've got a sequence of numbers. This one right here is what confuses some people if you ever see 0 factorial. So I'm going to do what I just did here, only backwards. So I'm going to start with 4 factorial, and I'm going to divide by 4 to get 3 factorial, divide by 3 to get 2 factorial, divide by 2 to get 1 factorial. So if I divide by 1, I get 0 factorial, and 1 divided by 1 is 1. 0 factorial is 1. So that's one thing that maybe might show up somewhere, but not on this test, but just somewhere in your life. Walking down the street, somebody needs to know what 0 factorial is. I don't know. Okay, so now let's find the value of E a different way. The value of E is equal to this series. A series is when you add together the terms of a sequence, when you add together all those elements in a sequence. And this sequence is 1 over n factorial. Okay, the series is when I add up all of the terms. So we're going to add up all of these terms. Can you do that easily? I know some of you can, but if you don't, I'm going to show you how to do it. Can you, like, you'd have to do 1 over 1 plus 1 over 1 plus 1 over 2 plus 1 over 6 plus, I mean, you could do that on your calculator. There's a shorter way of adding together. We're dying. You guys want to open a window or something? If you're having trouble, it's kind of warm in here. If you're having trouble staying awake, stand. Go find a desk or counter and stand. We did not cover series and sequences in here, but you should know this symbol. Did you do that last year? So I'm going to use this symbol, and I'm going to set it up so I don't have to do this by typing in a bunch of fractions on my calculator. Plus, this goes on forever. So on my calculator, it's going to be a variable. This is the part where if you have an 83, you won't be able to type it in the way I do. If you'd like to know how to type it in your calculator and you have an 83, you see me later. Okay. Everybody else should be able to type it in. But on the calculator, there is a summation symbol. Before I go to my calculator, you just decide what variable you want to use. It could be any letter. I'm kind of boring and lazy, so I'm just going to use X. And you want to decide what number X is going to start at. So X is going to be our variable. And when I look at all of these terms, when I look at each of these, the thing that is varying, the thing that is changing is the bottom. So what should I make my X's be for the very first term? 0. You can make it be 0. So I'm going to make my X be 0. Now, this is going to keep adding forever. I'm not going to keep adding it forever. So maybe I will just start out by saying 7 will be my last one, just because that's what they have so far. But I will go back and change that. And then out here, I need what formula gives me each individual term. So that's going to be 1 over X factorial. So I'm just plugging in each X one at a time, but I'm going to have the calculator do the work for me. So to do it on your calculator, you're going to go under math, and it's easier to scroll up, and you will see summation. So if you don't have this on your calculator, you won't be able to do what I'm doing right now. You have to do it a different way. The 83s don't have it. At the bottom, I'm just going to say, I'm going to make it X. It's going to start at 0. I go up to the top, and I said I was going to stop at 7. In here, I'm going to go ahead and, inside, I'm going to make that a fraction. So just remember alpha y equals, enter, 1 over, and it's going to be X, and then factorial. Factorial is under math, probability, number 4. Oh, shoot. I need to do that so it's not a fraction, because it'll give me a fraction answer. Hold on a second. I'm just going to make it 1 divided by instead of 1 over. mean, you can just change it to a decimal also. I forgot I'll do that. Okay. So that's through the 7th x, which is how many terms? How many terms? It added up 8 terms. So now I'm just going to hit like second enter, or you can go up and grab it. I'm going to change that 7 into, how about a 10? Why not? So just add in a few more terms. Okay, and then I will change it again to, I don't know, a 15. And then I'll try a 20. And I just got 2 of them in a row that were the exact same answer. And we've already looked, this is E. So this is another way of deriving E, somewhere that it shows up in real math calculations. You guys remember doing asymptotes at some point? Asymptotes. So this is kind of like, it's not an asymptote, but that's kind of what's happening is this graph is getting closer and closer and closer, or these numbers are getting closer and closer and closer and closer to a specific number, which is E. So what's the approximate value of E? 2.718 plus some decimals, but that's good enough. So now that's all we're doing with deriving. We're not going to be tested on deriving. You're just going to have E pop up in some of the questions, and we are going to graph E later in the week. We're going to graph it. So you just need to know how we got the number from this. All right, so you guys can go ahead and open up the second part of the notes. Can anybody tell me this answer?
5.
It is 5. It's not plus minus 5. This is 5. Do you know the difference of why it's not plus minus? Because there's no plus minus in front of it. That's totally true. Like, when would we have a plus minus in front of it besides it was just there? Yes. If there's an equation and you are square rooting both sides, this would be a place where I don't know what x is. X could be either. So this is where I would use the plus minus. But if I just say, hey, find the square root of 25, I've already told you I want the positive square root of 25 because there's nothing in front of the square root. Okay, so here's the hard question. How did you know that that symbol told you to make it 5? How did you know square root meant to find 5? How do you know what the square root means to do?
Fifth grade math teacher told me.
Because who told you?
5th grade math.
5th grade math teacher told you. And at the time, were you like, this is so hard, I'm never going to get it? Did that happen at the time? Maybe. I don't even remember learning square roots. I just like know them. And I know I didn't come out of my mom knowing what they are, right? You're not born with it. This is something you learned. So when I'm talking about logs, people always get scared about logs or don't remember things. Log is just something that you were introduced to for the first time last year. And the more you use it, you're going to remember what it means, and it's just going to be like easy. So it's all about consistent practice, and then it's not going to be a hard thing. It's just like having a square root symbol, or gosh, go way, way back. And I know you're not going to remember how you learned this, but like, oh, my thing stopped working. Back in the day, how did you know that that meant to put all those numbers together and make it 8? How did you know that symbol meant that? Not when, but you learned it and you practiced it. Therefore, it stuck with you. That's what log is going to do. You've done it for 1 year, not the greatest year to do it. I don't know at what point you guys learned it, if you were on.
Yeah, we learned it in person.
You were probably in person, yeah. Because I would say my classes were in person too.
It was like
Oh yeah, definitely that was out of class for sure. Okay, so today we're doing logarithms, and logarithms. A logarithm is the power to which a number must be raised to get another number. The logarithm is an exponent. It's an exponent. Going back to the second example that I put up here when I put in the plus minus, how or why, I don't know. Why did I use the square root symbol to solve this equation? Why did I use that? Emily? Because square root undoes, it's the inverse of squared. They undo each other. So logarithm is an inverse of something you already know. Logarithm is an inverse of exponential stuff, okay? So logarithm is the inverse of exponential. Oh, and I have that written right here. Inverse equations of exponentials. Now, 2 to the x equals 16. You all better be able to tell me what x is in your head. Yeah, but like out loud, I mean. You find it in your head, say it out loud. What is it? 4. Okay, we know the answer. I would never use logarithms for this. However, I'm going to use logarithms to show you how logarithms work, if you have forgotten. So 2 to the x equals 16. 2 to the x is an exponential. What I want is x by itself. To get x by itself, I need to cancel out that base of a 2. How I cancel out a base of 2 is I do the inverse of base of 2. The inverse of base of 2 is log with a tiny little, it looks like a subscript, base 2. Log base 2 will cancel out the 2 of 2 to the x because they're inverses. If I do it to one side of the equation, I have to do the exact same thing to the other side of the equation. Oops. We're going to worry about later why this becomes x. But the log base 2 of a base of 2 are inverses and they cancel each other out. So now I have x isolated by itself. I just need to evaluate the other side. So evaluate would be finding one value. Evaluate, we're going to find one value. So instead of log base 2 of 16, we're going to find what that value is. Now I said log is finding the exponent. So what you want to think about here is I cannot change what base is on the log, but I can use substitution to get rid of 16 and make that 2 to some power. What is 16? 2 to the what power? 4. When I make that 2 to the 4th, log base 2 and a base of 2 undo each other. They're inverses. And now I have x equals 4. Which we knew already, and yes, I would never use logarithms to do this question because that takes way too long.
So it's log with a little 2 because it's 2 to the x power.
It is log with a base of 2 because that's what will cancel out the big base of 2. So you can do log of any base you want, but I chose my base because I wanted it to cancel.
So like if it was 3 to the x power, you would do log base 3.
Oh yeah, let's see what the, look, the next question. 3 to the x power, sorry, yeah, we're gonna do that one. So looking at this next question, Emily's way ahead of us. So here I wanna get rid of the base of 3 so I can get x by itself. So I'm going to log both sides with a log base 3. Do we know the answer to this already, by the way? What is it? Yes. What is it? The original. It's 4, yeah. So when I use my logarithm, I get x equals log base 3 of 81. So at this point, we need to evaluate. And I'm going to change log base 3 of 81 to log base 3 of 3 to what power? 4. And that's how I get just the answer of 4 by itself using logarithms. Now, this will be more helpful when we have questions that you can't use logarithm, that you can't do in your head, like 5 to the x equals 7. When you have 5 to the x equals 7, that one I can't do in my head. Okay, the next example is a different set of directions, and I don't have the directions there. So the directions are evaluate. Evaluate. So we're just finding one value for this. In order to evaluate, we need the word log to go away. So what I need to do is I can't change the little base on the log, but I can change the 1/16 to 4 to some exponent. So when we do the log, we're finding the exponent. So 4 to the what is going to give me a fraction. Negative. 4 to the what gives me 16. So -2 would be, ooh, that was yucky. -2 would be my evaluated answer. Okay, there's no x equals here. It's just a number that is equal to that. And then this one is the same way. So we're going to rewrite this as log base 7 of 7. And the question is, what is the exponent? It has to be the same as the base so that I can cancel them. So you have to tell me what exponent makes 7 to the what power gives me 1? What is it? 0. So 7 to the 0 is what gives me 1. So my answer for this question is just, I was trying to do it in a different color. My answer is just 0. Okay. Now I'm going to go up and do that warm up that I skipped before. Or we are going to go up and do the warm up. So now you don't need to use logarithms for this, however you could. But can anybody figure out what the exponent is that makes this true? If I start with a 2 and I raise it to an exponent, how does it become a -8? Christopher, you want to share something? No, you don't want to. Megan, what are you thinking? Nothing. It's all like blank in there. No. 2 raised to a power gives me a negative number. What exponent is going to change it into a negative number? What? Okay, somebody volunteer what they're saying. I can't understand what the masks and people talk at the same time. Barry, you wanted to say. Okay, so what does a negative exponent do? It flips it. It makes it into a reciprocal. So this would be 1/8. Not -3. Marie, do you know? Peyton? Where's somebody volunteering? Because it's impossible? Okay, well then just tell me that. There isn't one. There isn't one. Were you going to say that, Ava? I don't know. Maybe we can find an imaginary number that works. I just haven't done that. But we're talking real answers here, okay? There isn't a real answer. There isn't a real answer. So the reason why I want to show you this is, if I actually use logarithms for this one, I would have to do log base 2 to both sides. and then I would get x equals log base 2 of -8. If I do that, there's no answer to this because there's absolutely no way I can take a positive number, raise it to an exponent, and have it turn into a negative number. That is impossible. There's another impossible thing. I cannot take a positive number, raise it to an exponent, and have it equal 0. That's another impossible thing. So in this case, like when we have logarithms, this always has to be greater than 0. Always. Always. And that's written in the next paragraph, but I wanted to show you why. So that's written in this next paragraph right here, where the x value has to be greater than 0. This first sentence is actually saying that if we have log base a of x equals y, it is the same as this exponential equation, a to the y equals x, as long as x is greater than 0. Now, you guys probably did some gimmick where you were like, whoop, whoop. Okay, I'm not doing the gimmick because when we do gimmicks, sometimes it works for one particular case, but then it doesn't work for every other case. So I'm going to use the mathematics to switch things around. If you remember what I'm talking about at all. If you remember that and it works and you use it, that's fine. That's just not how I'm going to teach it. There's 2 logarithms that are kind of important. If the base is not given, if it just says log, like this example right here, if it just says log, it is called the common logarithm. And the common logarithm has a base of 10. We just don't write it. That's just like when we do a square root, we don't put the little 2 in there because we just know it's a square root. So this log, we just know it's a base of 10. And that log is on your calculator as a button. And oh my gosh, look at that log button on your calculator. Look at this, so cool. This log button, what is right above that when you hit second log? A base of 10, and they're inverses of each other. Not coincidental. Okay, so let me simplify this or evaluate, or let's evaluate it together. To evaluate, we need to we don't change the base of the log, we change the big number. We change 1/100 to a base of 10. So 10 to what exponent is going to be 1/100? -2. So that's evaluated log of 1/100th. So the next one has an ln. ln stands for natural logarithm. The ln is log of base e, which is the natural base. So e is the natural base. Log base e is the natural logarithm. So ln stands for natural logarithm. But ln is natural logarithm. The L and the N don't stand for NL. It stands for something else, but it's probably like Latin that stands for natural logarithm or something. Okay, so if I have an ln and I'm doing a natural logarithm of the natural base, guess what those two things are? They're inverses. So guess what they do? They cancel and I just get 3x here. And if you look at your calculator at that e to the x button, ln is on the same button. ln and e to the x are the same button because they're inverses of each other. Not coincidental. I think square root and squared is on the same button, aren't they? Yeah, I was going to say those are inverses too. Not everything worked out that well in the calculator. Okay, so for example 1, change from logarithmic form to exponential notation. We're going to do something that's called exponentiate each side of the equation. We're going to do something called exponentiate. You are not solving. It does not say anything about evaluating. It does not say anything about solving. It says change the form. So what I'm doing here is not a real life application. This is just practice of changing forms so that you could apply it to a real life application later. So this is not a real life application. To exponentiate both sides, if I have a logarithm, exponentiating will get rid of the word log. It'll change it into the other form. So when I want to exponentiate, I say, what is the inverse of log base 7? And you guys are going to tell me it's a big 7 with an exponent. That's the inverse of log base 7 is a big base 7 with an exponent. So what I do to both sides of this is I'm going to make a big base 7. And as long as I do it to both sides, I can do whatever I want. So I'm going to take log base 7 of 343 and make it the exponent. And then on the other side, do the exact same thing. Big 7 to the third. Now, when I do that, 7 and log base 7 are inverses. They cancel. And I get 343. On the other side, 7 to the third. Now it's in exponential format. So the little swoopy thing that you guys learned before, that's what I just did, only I did it with like math rather than a gimmick. Okay? So now, anytime that I want to change from logarithm and not be in logarithm form anymore, I'm going to do exponentiating. Question? No. All we're doing is switching the form. We're not doing any extra work. Just literally switching it so now it's exponential form. Okay? So don't do any extra work. On your assignment, you're going to actually type some things into Canvas, and don't freak out because I got more information about that later. But you'd literally type into Canvas 343 equals 7 caret 3. That's what I type in Canvas. Okay? All right, so the next one, same thing. We're going to exponentiate because this is logarithmic. What is the base? 10. So I'm going to do 10 to the log of 10,000 equals 10 to the fourth. So I get 10,000 equals 10 to the fourth. I mean, you can say, oh yeah, that does equal it. That's one way you know you did it right, is it should be true. But that's all I'm asking you to do. So the third one, this one has a variable in it. I'm not asking you to solve it. It's actually already solved for y. I'm just asking you to switch the form. So what will we exponentiate with? Ryan, what will I exponentiate with for C? Well, what is the base? Then what will I exponentiate with? The base. 3. Okay? You guys pay attention, you will know exactly what's going on. If you're doing other things, not that Ryan is, but if you're doing other things, you're going to miss something. So I'm going to exponentiate both sides. 3 to the y, 3 to the log base 3 of 5. So the log base 3, the 3 to the log base 3, those are inverses. They undo each other. And I have 3 to the y equals 5. So I'm not solving something because that would basically be unsolving it at that point. Just switching the form. Again, why are we doing this? Just so we know how to do it for when it gets more complicated. Next section is change from exponential to logarithmic notation. So if we're changing to logarithmic notation, you're going to do what's called log both sides. That means you're going to put log in both sides. We've already done this. We're going to put log in both sides. So for the first one, what is the base? Madeline, what's the base for question A? 6. So I'm going to do log base 6 to both sides. I get 0 equals log base 6 of 1. Done. Change the format. Sam, I'm going to change B into logarithmic form. What should I do to both sides? Okay, so I'm not going to write log base 10. What am I going to write? Just log. Good. It is log base 10. You're totally correct. But I'm just going to write log because that's what we do. So log base 10 and 10 cancel. We get -3 equals log of 0.001. And that's it. That's all you have to do. So last one, what base, Philip? What base for C? Should I log? I should do log of what base? 2's not a base on a power. 16. So we need to use the base that actually has a power. And that's all you have to do. You don't have to solve anything. You don't have to simplify anything. That's it. Okay. The next section, now we are going to simplify, but it's without the use of a calculator. So this we did as some of the very first examples. These are evaluate, simplify, evaluate, same thing for this. We're going to find one number. So log base 5 of 125, we're basically finding log base 5 of 5 to what exponent? That's what we're finding. Jack, what exponent on the 5 is going to give me 125? 3. So these cancel and we get 3 for our answer. It's just the exponent. That's what the answer is. The next one looks a little funny. What is it when it's just log by itself? Eden, what's it when it's just log by itself? Right, it's log base 10. If it's bothering you because you can't like envision the 10, just put it in there. Log base 10, and then I need to make this 10 to an exponent. And I'm finding the exponent. 10 to what exponent will equal the number 1? 0. Anything to the 0 power equals 1. So if it has a 1 in that place, it's always going to be 0. Okay, so this one, if 32 is the base on the log, I can't change that number. I can only change the big number, the 2. So I'm going to make that 32. But to what exponent is actually making it equivalent to 2? Sanjay? Oh, I didn't hear you say. Yes, 1/5. So that's the answer here. So if I'm like showing all my work, I would figure out that it was 1/5. And then I would cancel out these 2 and get just 1/5 left over. All right, so question D. Patrick, can you tell me the answer to question D? It is just 1. And I'm glad that you came up with 1 because some people just are like, there's nothing there. But we have to remember that the definition of a log is like, what is the exponent? So when the exponent is 1, we don't write it. So we just got to be careful and remember there is a 1 there. How about E? Tyler. -4 is correct. If you guys are ahead of me, that's totally fine. I'm just like calling on people because I don't want the same people answering every single time. All right. F. Ava. It is impossible. So since I am not solving, by the way, it's impossible. We can't do a logarithm of a negative number or 0. So where that -4 is, can't do it. Since it's impossible and I'm not solving, I'm not going to write no solution. I'm just going to write undefined. You would write no solution if we were solving. Oh, look, the next ones are solving. Yes. Sure. I feel like none of them are undefined for the, I don't think, so where we're going to have that situation is when we start solving it and there's, I mean, we're going to get to it today, but when we start solving it and there's, what's the word? Extraneous solutions, that's where we might have one that doesn't work and one that does. And so then you'd have an answer. Or if none of them worked, it'd be no solution. I don't think I gave any that are just undefined. If so, then I'm sure UNDF is fine. I would have said it on there, but I don't think any of them are. Okay, going back to this. So solving, goal is to get x by itself. We follow our rules that we always follow for solving an equation. Get x by itself. Get rid of the other stuff that's around x. What's the first thing I need to get rid of for question A to start getting x by itself? What is the outermost thing being done to x? That's not the last thing being done to x. There's something further out. It's the log. So that's the first thing I'm going to get rid of. How do we get rid of log base 3? Starts with an E. We need to go back and look at the word. It is exponentiate. Let's all say it together. Ready? Exponentiate. One more time. Let's practice it. Exponentiate. Doesn't that make you sound so fancy? No? Okay. It makes me sound fancy, so I like to say it. It's a big word. I didn't get a 36 on my ACT, so I need to practice those big words. All right. So we're going to exponentiate both sides. Oh, I'm totally jealous. That's for sure. We're going to do it base of 3. I'm going to do 3 to the log base 3 of x minus 3 equals 3 to the 5. Do that to both sides. That's going to cancel out the log base 3. That's going to leave me with x minus 3 equals 243. So x is 246. How do I know that's true? Check it. Okay, that one's easy to check. I plug it back in, it works. Okay. We're not going to spend a ton of time on checking. The next one, we need to get x by itself. This is a little trickier. I didn't give you anything where the x was the base. Okay, it's a little bit trickier. So sometimes if you're totally like stuck on what to do, maybe just change the format from logarithmic form to exponential form. Maybe that'll give you an idea of what to do. If not, then just erase that step and figure something else out. But that would be a suggestion of mine. Let's change the format into exponential form. How do I get rid of logs and change it into exponential? Abby? Evans? Good. So she's going to exponentiate both sides with a big old X. Both sides. Right? So then that cancels out x to the log base x, and we get 343 equals x to the 3/2. Now what comes is old algebra 2 review. How do I solve this equation for x? Square both sides? Is that what you said? You have to like, and then do that. Yeah, I am going to square both sides, but I'm going to do two things at the exact same time. So instead of just squaring both sides, I'm also going to cube root at the same time. I'm going to raise both sides to the 2/3 power. Because when I when I raise an exponent or a power to a power, when I raise power to a power, I multiply my exponents, which gives me x to the first power. Now, 343 is powers of 7. That one you might not be as familiar with, but you'll see it a couple times today, so maybe you'll remember. 343 is 7 to the 3rd. And if I have 7 to the 3rd and then take that to the 2/3 power, I get 7 squared. So x is 49. And that's without a calculator. That's me knowing what 343 is and then playing around with my exponents. Question.
So we simplify when there's an exponent as a fraction.
Yes. If it's possible. This one is possible. Yeah. Okay, the next one, we need to get x by itself. Get x by itself. Abigail. What should we do to both sides? Mm-hmm. You remember the fancy word we said together a couple times? Yeah, exponentiate. Good. Okay, I'm going to simplify some stuff. Those cancel out. I get x squared minus 12x equals 64. Did I go too fast? Okay, from here, what should we do? We just got to solve stuff from algebra 2 now. Eh? Did you say subtract? Okay. Because what are you trying to do after that? Factor? Hopefully it factors, right? Oh, yeah, it does. And I get x equals 16, and I get x equals negative 4. So this makes me a little nervous because I got a negative number. So I'm going to check them. If I plug in 16, and I do 16 times 16 minus 12, that's 64 total, and that would be 30. What happens if I plug in a negative 4 into that logarithm? I get negative 4 times, does it? I get negative 4 times negative 16, which is positive 64, right? So log base 4 positive 64 is 3. That's true. So they both do work. You just got to check and make sure. So we have two answers, negative 4, positive 16. All right, two more of these, and we're going to take a quick break, and then we're going to finish. Okay. This one has ln. We mentioned ln earlier. ln is a log. So this is in logarithmic form. We need to get x by itself. What do I do to both sides if it's in logarithmic form? It starts with an e. You're going to exponentiate, but what should the base be? E. Is that what you're going to say? E. So I'm going to do e to the ln of 2x minus 3 equals e to the ln 11. Well, the e on both sides cancels with the ln on both sides. We get 2x minus, oh, that was so messy. We get 2x minus 3 equals 11. And then from there, just solve that equation and check it. Okay. Last little example here. We've got 5 plus e to the x plus 1 equals 20. Lainey, have I called on you yet? I mean, you've answered. I don't know if I actually called on you. What should we do first? Thank you. You would need to subtract 5. You do not try to cancel out that e when there's other stuff there. It will not work. So make sure you subtract that 5 first. It's the same way you would solve any other equation. It just has an e in it this time. So now what is going to cancel out e so that we will get that exponent by itself? Natural log is the inverse of e. So we're going to log both sides with ln. I'm going to do ln of e to the x plus 1 and ln 15. Cancel, cancel. X plus 1 equals ln 15. So x is ln 15 minus 1. So that's like the exact answer. I could find an approximate answer with my calculator, but I don't need to. Okay, you're taking a quick brain break. Put your stuff downstairs. All right, the last section of our notes for today is we're just going to start talking about properties of logarithms, which if you got stuck last year on logarithms, this is usually the part people get stuck on. We're not going to do like the hardest part of it today. We'll just save that for next class. We're going to do an easy part of it today. Properties of logarithms are related to properties of exponents because they're inverses of each other. For example, if I do x to the second multiplied by x to the third, they have the same base. What do I do to their exponents? I add them. Well, if we look at our product rule for logarithms, I'm going to look at this side first. If I have separate logarithms with the same base that are being added, I can condense that to one logarithm with that base, but I'm going to multiply the pieces together. So that's kind of opposite of what's happening in exponents. They're related. Like in exponents, when we multiply, we add them. Here, when we're logarithms, if we go from multiplication, then we go to adding. Quotient rule, if I have like x to the 7th over x to the 3rd, I would get x to the 7 minus 3, which is x to the 4th. So I would subtract. So the same thing with logarithms. If I'm dividing what the logarithm is of, I can separate it to have separate logarithms subtract. Or if I have separate logarithms subtracting, we can condense it. This power rule has to do with, like, if I have x to the 3rd to the 5th, if I've got power of a power, what do we do to the exponents here? We multiply them, right? So we have a power in logarithms. Here's my power, p. What ends up happening is I'm going to pull it out front and I'm going to multiply it. So that's where it is right here, multiplied with the logarithm. So if we have an exponent on what the log is of, it becomes multiplication of the entire log. I'm going to give you a really quick example of how we've actually done that a ton today. I just didn't tell you it was a property. What did we have? We had like log base 2 of 2 to the 4th. That was like one of the first things we did. And remember how we just canceled this out and said it was 4? Well, like, what really makes it a big 4? Because the property is actually, we're going to take this 4, we're going to put it in front, and we're going to multiply it by the answer of this, which is 1. I just, without knowing the properties, I don't want to teach that right off the bat. So that is a property. And that's why it works every single time. And then the last, it's not a property, it's just a rule. And it becomes important in calculus when you're doing derivatives, which is half of what you do in calculus. Change of base rule says if we have log base b of m, you can take any base you want. They chose A. You can take any base you want and write the log of that base of m divided by the log of that base of b, and it will be equivalent. So if I had something like, actually we have some down here. Let's look at the log bases, this down here. Use the change of base rule to evaluate this. If I have log base 5 of 7, I can change this to any base that I want. And there just happen to be a couple logarithm buttons on here that I think are convenient. What logarithm could I change this to? If I want to pick any base I want, what base could I possibly use? Base what? Did I hear 10? Did I hear 10? So log base 10 is just log. We have a button on our calculator. So I could rewrite this as log base 10 of 7 over log base 10 of 5. And then I can get the answer to that really easily. There's another different base on the buttons of our calculator, which from what I've heard or remember comes up more often in calculus. So there's another base on here that comes up more often. Do you know what base it is? We learned about it today. It's the log base e, which is ln. So ln of 7 over ln of 5 is the exact same answer. And really, you could do any base you want, but there aren't a lot of bases that are convenient. Like we could do log base, I don't know, 11 of 7 over log base 11 of 5, and it will be the same answer. But that one's too complicated to type in. So if you are asked to do change of base rule, you need to be able to show me either this or that. You need to be able to show me that you know what that rule is. because it will be important later. And then you just type it in your calculator. Log 7 divided by log 5. 1.2091. Make sure you know how to type that in your calculator. Just because I can do it doesn't mean you can. Did you try it? Did you try it? I don't believe all of you. So for this one, we're going to do change of base. It doesn't matter if you use log base 10 or if you use ln. It doesn't matter. But you should be able to write what the change of base is. And then just make sure we know how to round correctly. That's always important too. Okay? Yes, Tyler.
You can calculate the log of any base on this thing without having to do that. It'll just.
Oh, I know that. That's not going to help you when you get to calculus and you have to do stuff with x's. So Tyler's bringing up a very good point. But when we are talking about using change of base, we just need to know that you know how to do change of base. But unfortunately, if you have an 83 calculator, you don't have what I'm about to do. So change of base is your only option on the 83s. But if you have the newer ones, yes, if you go to math and then you go, I just go up to A, there's log base, and we can put in that 5 and that 7 right away and find the answer. But again, when there's x's in there and you're solving equations, you're going to want to know the log base formula, the change of base formula. Okay? Thanks for saying that. All right. And then what did you do? I am skipping these examples for next class, and I'm just doing these last 2 examples because this is what the assignment's going to look like. This is all we're going to use the properties for today, is solving these equations. This is all we're going to use the properties for. We'll do more with properties next time because those get confusing. So we're going to use the properties of logarithms to solve this equation. When you have separate logarithms, you can't exponentiate both sides. You can't do the exponentiate when there's a sum of logarithms. Or on this next one, if there's a difference of logarithms, you can't exponentiate that entire side. So we have to condense it. So we're going to use those first 2 properties in tonight's assignment. The first property says, if I'm adding the logarithms, I'm going to have 1 logarithm and just multiply their stuff. If I'm subtracting the logarithms, we're going to have 1 logarithm and divide their stuff. So my first step for question A is going to be the 1 logarithm, log base 7. And then I'm going to multiply together x minus 2, x plus 3, and I'm doing it really fast. X squared plus x minus 6. So we have 1 logarithm now. When we have 1 logarithm, now we can exponentiate. What base should I choose? Ryan. That is not a base. I want 7. So I'm going to exponentiate by making both sides 7 to that entire side. 7 to that entire side. I just went like really fast and didn't rewrite it. So now I have x squared plus x minus 6 equals 14. I'm going to finish this. If you have to leave, I get it. But I'm recording the video. You can always go back and watch it. So now I'm going to move that 20 over. But if you are leaving, just do it quietly. I'm going to move that 20 over and factor. And I get 2 solutions. So when we have 2 solutions, anytime we have solutions. We want to check and just make sure that we don't have any extraneous solutions. When we had 2 solutions before, they both worked. When we had 2 solutions before, they both worked. Will these both work? If I plug in -5, plug it into the original question. I'm going to go right here. I'm going to plug in -5. And right now I have log base 7 of -7. Guess what? I can stop. That one can't be an answer. Now, it works if you plug it in further down, but it doesn't work there. So if it doesn't work in the original, it's extraneous. Goodbye. And then you plug in 4. 4 does work. Okay, good. Okay. So just make sure we're checking for extraneous solutions. So then this last one, we've got log base 2s, and it's subtracting. So we are going to condense that with division. And Philip, I need to get rid of log base 2 so I get the x by itself. What can I do to both sides? I'm going to exponentiate. So 2 to the power of that and 2 to the power of that. So that'll cancel, and we get x plus 1 over x minus 4 equals 8. And now it's just like, do you remember your algebra 2 skills? Can we cross multiply or multiply both sides by x minus 4 and solve? This one does work out to be 33/7. I've checked it, trust me. You can check your own when you're doing your assignment. So you'll have just like a few questions like question A and B here. So the people that left, I really hope that they watch this or at least pay attention. The assignment for today is do as much as you need for a quiz next class. So you don't have to do all of it. The first upload is up and ready, and I'll have the second one up after school. I just didn't have time to put it up yet. But the first upload is the kind where you'll type it in, and I want you to practice some of that so you know what to do on the quiz about typing it in. So it's not like a big surprise. The second one, I'll just put all my work. The second one is like the solving equations that we just did at the end. Yeah, just do as much as you need because we're having a quiz next class. That's really going to tell me if you understood it, and that's worth more anyway. So just do as much as you need. There is a problem-solving worksheet that isn't due till April 12th, and that is not do as much as you need. That is do all. But today's assignment is do as much as you want. Okay?